Hello, everyone. Thank you all for coming today. It is fabulous to see you all here. And it's a true pleasure and an honor to be introducing our speaker for this year's Welsh colloquium. My name is Professor Miriam Diamond, and I'm an experimental astroparticle physicist here in the U of T physics department. And I get the rare opportunity to introduce you to one of my wonderful mentors, Professor Anthony Noble. So he is a professor of physics at Queen's University and a Canadian research chair in particle astrophysics. He obtained a BSc in physics and math from the University of New Brunswick in 1983, and his doctorate in 1990 in particle physics from the University of British Columbia. In his doctoral work, he measured a very rare decay of a particle with a strange quark inside it, which was one of the first strange things he did in his career. No, actually, then he went to CERN, where he helped make some measurements of what had become at the time quite a zoo of elementary particles, and thereby helped add several critters to the zoo. In the late 1990s, he then joined the Sudbury Neutrino Observatory Experiment, or SNO as we called it, 2 kilometers underground in an active mine. He quickly emerged as one of the leaders of the team, becoming the associate director responsible for the systems that purified the very large amounts of heavy water used in the experiment. The SNO team quickly solved what at that time was called the solar neutrino problem, which was that it seemed like too many neutrinos were predicted to come from the sun compared to what we were actually detecting. SNO showed us that, in fact, the sun was producing exactly the right number of neutrinos, but the neutrinos were changing from one flavor to another as they journeyed from the sun to Earth. So we actually need to be able to detect all 3 neutrino flavors in order to catch them all. This work was what led the SNO director, Arthur MacDonald, to the 2015 Nobel Prize in Physics, thanks in part to the other Nobel in the picture, Tony. Yes, pronounced Noble, not Nobel. After the great success of SNO, Tony then took a lead role in the transformation of the SNO experiment into SNOLAB, which can support several experiments at once that require shielding from cosmic rays and a very clean environment. Among these experiments are some that search for dark matter. And he will be talking about one of these in particular, PICO, not to be confused with Pikachu from Pokemon, even though the goal is eventually to catch them all, them being all the types of subatomic particles that exist. Yes. Tony's leadership helped establish SNOLAB as one of the world's leading underground laboratories. And in 2016, Tony became the founder and scientific director of the MacDonald Institute, with a mandate to coordinate and advance astroparticle physics in Canada in partnership with 11 universities, including U of T, and 6 research institutes all across the country. The MacDonald Institute has really transformed particle astrophysics in Canada, addressing some of the most fundamental questions in our understanding of the universe. And he will be talking about some of these very questions today. So please join me in welcoming Professor Tony Noble.
Okay, thank you. A question to you guys. Do you have a way of removing the stop share thingy? which will be just a little bit annoying as I was sitting there. So one of the best things about the McDonald Institute is Miriam. Miriam, we were able to hire 15 new faculty all across Canada, and Miriam was one of them. And I decided to forgo the tie, which is blatantly advertising SNOLAB yesterday, and instead go for my McDonald Institute shirt. So there'll be maybe a test at the end if you can identify all the different experiments that we support. Working. Okay, so yeah, so yesterday I talked about neutrinos. Despite being the director, I'm still very active, or try to be very active, is probably the better way of explaining it, on some of the research that's happening underground. When I started the McDonald Institute, the reason I started it was, as Miriam mentioned, we went from the SNO experiment, a single experiment with a dedicated cavity, to this big campus where we're hosting now dozens of experiments. And what I discovered was that Canadians were very busy and very active and engaged in running the facility to make it work. And we weren't sufficiently engaged in the science. And so that was the purpose of creating the McDonald Institute. We went from sort of about 20 or 30 people on my Rolodex who were vaguely interested in astroparticle physics in those days to now over 100, in part by hiring 15 new faculty directly, but then all the subsequent knock-on effects, the population has just grown. So now Canadians are leading in the science, not just being caretakers of a facility. Okay, that has nothing to do with my lecture, but since you mentioned the McDonald Institute. So I'm going to talk about the PICO experiment, which is a kind of an odd experiment. It has a very different technique for looking for dark matter compared to many. And so I'm going to talk what makes that so special about the bubble chamber technology. So it's a reinvention of a technology that existed, 50, 60 years ago, largely died. And most bubble chambers you will see now in the parking lots as statues and mementos and whatnot. But we've reinvented that technology for the use for PICO. So I'm going to talk about that. But I'm going to start by just motivating things a little bit in terms of and I'll go over this quickly because I'm sure people are fairly convinced that the evidence for dark matter is there. And so I'm going to talk, there's a number of different ways you could motivate this. I put here galaxy rotation curves. That's the easiest one to understand. So I'm going to go over that one just to show that. Gravitational lensing. I really like this bullet cluster one where galaxy clusters have collided, and then you can follow the mass and you find there has to be dark matter. And cosmic microwave background. I'll talk a little bit about this one as well. So rotation curves, and I apologize, this is going to be seem a little bit basic, but I show this because this is what I show when I go to high schools and so on, how easy it is to predict dark matter. And so if you start with the solar system, and at the high school level, people are already knowing force of gravity, gm1 m2 over r squared. Everybody knows the centripetal force is mv squared over r. And that allows you to very simply, because these are the same forces, we go here, make sure that's working. So you can solve for v, right? And when you solve for v, you get this relationship that just says that as a function of r, so when you get further and further away from the sun, the velocity should go down. And you can look up, well, first of all, you can just plot that. And if you plot that, you get this curve, which says what the planets should do if they behave this relationship. And if you then stick the planets on, you see a remarkable agreement. And this is something that you can do when you go to high schools and stuff like that. You can see I've done this a long time ago because Pluto is still on there as one of the planets. But it's just a perfect fit, right? Even though these aren't actually perfectly circular orbits and so on, it's good enough. The situation is the same when you start thinking about a galaxy. The difference is that in a galaxy, all the mass is a little bit more extended than the sun. So we don't have quite that perfect thing where we have a point of mass, but we have a galaxy, and it seems to kind of end around here, right? But if you plot the velocities, and I'll put the sun on there just for reference, or somewhere out here, But if you plot the velocity, it doesn't drop down like you would expect once you get outside the galaxy. You see that, in fact, this one is slightly increasing. That's the observed likelihood. Now, there aren't a lot of stars out here, so this is mostly the dust and things, people looking at the 21 centimeter line. But they're measuring the velocity of stuff that's in orbit around the galaxy, and it's going way too fast. What you would have expected is that it would drop off, something like this. And if we went back to the first slide I had a picture with many tens of galaxies that all show this behavior. It's a very consistent behavior. It's not special to this one. That the rotation curves say the things out here are going far too fast. They should be thrown out of the galaxy, and they're not. Something is holding them in, but there's not enough mass in the galaxy in terms of what we can see visibly to hold them there. So that's where the idea came from, that there's some other mass hidden in the galaxy. It's not producing light. And that's where the idea of dark matter came from. That dark matter is giving the gravitational oomph to keep those things in rather than being thrown out. Okay, so there's clearly a lot of mass outside the visible galaxy, and that's what we conclude is dark matter. So that's a very easy one for people to understand. And somehow I've lost the ability for this clicker to do anything, so just work from here. So the cosmic microwave background was the second one I wanted to use. And this one is really dangerous for me because I'm in a room filled with experts on the cosmic microwave background. And I said last night at dinner, I'm not sure I should put this in with all those experts there because my understanding is nowhere near theirs. But they said, go for it. See what you can do. We'll see what you know. So anyway, let's see this. So this is an experimentalist's understanding of the cosmic microwave background. So at one time, and deliberately I put 350,000 years old before the 380 magic date, we can consider the universe was this very homogeneous plasma. And somehow, when we look at the sky now, it doesn't look very homogeneous, right? It looks like it's all clumpy with stars and galaxies and everything all over the place. So the question is, how did we move from that phase to what we see now, 13 billion years later, and how could that be related to dark matter? Okay, so as I said, roughly 350 years ago, the early universe is very homogeneous. It's this ionized plasma. If you were to look inside here, you would see that the electrons cannot attach. They're bouncing around in this plasma, so the protons and the electrons, every time they try and attach, the energy in the system just knocks them off again. And so you're constantly in this plasma. And in that case, light can't get out. So light is bouncing around in the space, and it's just always hitting things, so it never really gets very far. So I actually asked the audience this question. So a related question is, how long does it take for the light to go from the center of the sun to the Earth? Anybody? No? Yeah? Eight.
About a billion years.
Okay, so we got 8 minutes and a billion years. Yeah. What's that? 100,000 years. Yeah, so it's a trick question. You're absolutely right. From the outside of the sun, it takes about 8 minutes. But from the inside of the sun, it's quite different because the inside is so hot, it's basically that hot plasma again. So the answer is not 8 minutes and 20 seconds. That's from the surface. But it's a hot, dense plasma. And I don't know how people measure these things, but the numbers we heard were two numbers we heard in the room today, somewhere between 100,000 and a million years, because the light is just bouncing around inside all the time. That's why when I talked about snow yesterday, it's really kind of cool. The neutrinos come straight out. So the neutrinos are probing what's happening in the core, where it's very difficult to interpret anything from light which has bounced around for a million years inside the sun before it eventually has a chance of escaping on a random bounce. Okay, so that was a little bit of a side, but it's exactly the same effect, and that was what was happening in the early universe. So then at about 300,000 years, sorry, 380,000 years, the universe is expanding, things are cooling, and at some point you go through this amazing phase transition that the electrons capture onto the hydrogen or onto the protons. You've now got hydrogen, and in this case, the light is now free to escape. And so the light, off it goes, And that's the light we see from the cosmic microwave background today. Now, as the universe continues to expand, they get stretched, their wavelength gets longer, their energy gets less. So now they're very low in energy compared to then. But that's what we can see from the cosmic microwave background. So you can sort of, this phase transition happens, the light comes out. So that's kind of our snapshot. That's what the universe looked like at roughly 380,000 years old. And that light, then we can study by measuring an isotropies of that, so how clustered it is, how clumpy it is, gives us a picture of how clumpy the original universe was and how that might lead to a clumpy universe now. And I'll show you the pictures, so rather than blabbing on. This is a map, a temperature map. So where it's red, it means it's slightly warmer. And where it's blue, it's slightly colder. But what I really mean slightly, these are sort of scaled, so we're showing differences at parts in 100,000 or so. So the very, very, very small deviation. So your first thought should be, if you just took a normal picture, you say, oh, it's completely uniform. But you keep zooming in, zooming in, zooming in, and eventually you see, it's not exactly uniform everywhere. It's kind of clumpy. And that clumpiness then are the seeds that would have led to galaxy structures. That's the idea. And so people study this, they map this, they measure. So on the top is the angular scale. So they map how, one clump is closer to another clump. And, you get this pattern, which is the dots. That's the data. And the green line is a fit. And that's what people in this room have dedicated their lives to, understanding how to make that fit and so on. It's amazing that the entire universe can basically be summed up in this plot with only about, 6 or 7 critical ingredients. I don't remember how many there are, and I know there's like 12 or so altogether. Some are fairly minor. But with just a very few parameters, you can fit these curves. And one of those bumps, the third bump, is responsible for explaining how much dark matter must be in your model in order to fit this. If you ever want to have some fun, there's a number of websites. The one I like is Max Tegmark's, who has movies where you can go in and you can say, I don't believe this. I'm going to change, the dark energy component or the dark matter. And you just tweak a number a little bit and you see the fit just goes wild. And, so that the fits are really, really sensitive to what the parameters are. And so, the amount of dark matter, as predicted by this, is a very robust measurement. Okay, so at the end of that, though, once you've done all these calculations, what we understand is that while we say we understand the universe extremely well, we actually understand about 5% of the universe reasonably well. And, the 27%, which is dark matter, we have no idea what it is. The dark energy, we really don't have any idea what it is. And the 5%, even that, most of it's dust and gases. That's about 4%. So what we know and what we think of the universe is about 1%. And sometimes it's hard to sleep, when you think about how much we don't know. So it's a huge industry. People are trying to explore what dark matter could be. These are simulations which show how dark matter would have formed these sort of, because it's gravitational, it's going to start clumping together and so on. And so you can imagine this. These are threads of dark matter in somebody's simulation where the dark matter is lying. And what's interesting is that's what drives where the galaxies go, because if I've got a hot spot here with lots of gravity, the baryons, the hydrogen is going to be attracted here. And so my galaxies are going to collect around hotspots. And you see, therefore, in that model, I get to get something that looks like the universe today. I understand this better if I think about pictures with cobwebs. You spray a cobweb with a little bit of mist, and the scaffold, which is the dark matter, attracts the water to the various nodes and so on. And so to me, that's a sort of analogy of what's happening with the dark matter. Okay, so what are the properties of dark matter? Well, we don't know very much. Let me just go through this. So first of all, it's neutral, because if it were a charged particle, it would be very easy to see. And so I'm just looking at the fundamental particles. We can expand beyond this, but if you look at just the standard model of physics and you say, okay, it's got to be neutral, that rules out a whole bunch of these things that are all charged. It's got to be at best weakly interacting. If it had electromagnetic interactions or strong interactions, probably we would have seen it, unless they're so strong it never got to us. But if it's probably weakly interacting, and in that case, we can get rid of the electromagnetic and strong bosons. It's massive because we know it interacts through gravity. So that gets rid of the photon again and the gluons. It's long-lived because, well, it's still around today, right? And so it's going to be long-lived, and so that gets rid of the Z boson. And, well, we've got neutrinos left, and actually there's great hope for a while. People thought that neutrinos might be the answer. Of course, they also thought neutrinos had zero mass, which doesn't work. But if they had a mass, then maybe that was the answer. But in fact, it's not the answer, we think, because the neutrinos are very relativistic. And you need to have the neutrinos moving very slowly in order that they push matter around, but not too much, in order for the galaxies to form in the way we see them now. So that neutrinos had a very big impact on the way galaxies form. But in order for that to work, what we call lambda cold dark matter has to be cold, which means it's moving slowly. That doesn't work for neutrinos. So you see, at least looking at the fundamental particles, there's nothing left. It doesn't seem to be any of those. There's also a lot of evidence that the dark matter is non-baryonic, which means it's not like a neutron or a proton. So you can't make combinations of these things to explain the dark matter. So we don't know what it is. It doesn't appear to be in our models. It looks like it's something new outside the models, and we're trying to detect it. Now, people have been trying to detect dark matter for decades. In fact, I have a copy of a talk given by Victor Zacek. I keep it on my desk. It's a photocopy of transparencies. Remember when talks were all done on transparencies, flipping over the project? And it starts out by saying, you know, physicists shouldn't be able to sleep at night not knowing what dark matter is. Nothing has changed. We're still trying to find dark matter. The experiments are much more sophisticated. We've ruled out a lot of parameter space, but we still don't know what it is, and it's still very difficult. And so I want to explain a little bit about why it's so difficult. Part of the reason is there's very little guidance from theory. So you might recognize this is Tim Tate's work, where he has tried to collect all the different models that people have come up with for what dark matter might be and put them into things like, are they axion-like? Are they related to small Higgs? Are we thinking about extra dimensions? Most of these things I don't even know what the words mean, but you get the picture that theorists are paid to be creative and they earn their money, right? There's a lot of different ideas on what dark matter could be, and we don't know. And if you were to say, okay, in your model, what's the mass of that dark matter particle? It would span 50 orders of magnitude in opinions on what that mass could be. And likewise, how does it interact? There's another 60 orders of magnitude in terms of the interaction strength, depending on what model you're in. So it's very difficult, and experimentalists have looked so far at, under the light post, where they think there's you know, if solving dark matter would also solve another problem, like we think maybe supersymmetry should be a thing in particle physics, that would predict a dark matter particle with a certain mass and a certain cross-section, so we can go and look there. So we've been looking in, quote, the most obvious places, and we're slowly starting to rule out this parameter space, but it's long, hard work. And again, largely because there's very little guidance as to what dark matter will be. Then how do you actually detect it? Well, if it's direct detection, which is what I'm talking about, your particle comes in, that's the symbol for a dark matter particle, comes in and it hits a nucleus, and the nucleus just gets nudged ever so slightly. So the amount of energy that nucleus has is in the keV range, and that's tiny, absolutely minuscule amount of energy. So you're trying to measure the tiniest energy deposits from one nucleus getting a little nudge inside your detector. So that's hard. You have to build detectors that are extremely sensitive to be able to see such an energy deposition. And you're doing that in a background where everything has radioactivity in it. Everything has some uranium and thorium in it. They're producing gammas and alphas and so on. There's neutrons all over the place when you're underground and on surface. So there's all these other things. If a neutron comes in and hits your nucleus, guess what? The nucleus is going to bounce, give it a little wiggle and deposit some energy. It looks exactly like a dark matter particle. How do I know I just didn't have a random neutron hit my nucleus rather than a dark matter particle? So an enormous amount of effort goes into controlling all of these things, measuring them independently so you know how much background you have, and as I say, trying to minimize it so that you have some chance of seeing the signal. So that's extremely hard. I'm going to give you a couple examples of the sorts of lengths people have to go through. This isn't necessarily true for PICO, but the first rule of thumb is you're all filthy. Everybody has about 140 grams of potassium inside. Normal potassium is not radioactive, but there's a very small fraction of potassium, which is potassium 40, and that is radioactive. And so a typical human body has 5,000 decays per second, just coming from the potassium in your body, which you get whenever you eat salt or whatever. It's perfectly normal, perfectly natural. But if you were to go stand beside Miriam's detector, it would just light up with the radioactivity from a person. So we have to get rid of all those materials that have radioactivity in them or control it at some level. One of the ways people like to control things is they put lead around it. Lead stops photons from going through, so that's great, and betas and so on. So if a layer of lead between you and Miriam's detector or you and the dentist when you're getting an x-ray, you know, that protects things. But lead is radioactive. And when you make a lead brick today, if you went to a smelter today and make a lead brick, it would have lots of normal lead in it, but also isotopes of lead that are radioactive. So you can wait it out. That will take you about 1,000 years or so for that radioactivity to decay away. And you'd have to make sure it didn't see any cosmic rays that might reactivate it. So there's a solution, and the solution is kind of neat, where there's something called ancient lead or Roman lead, which is that old Spanish galleons thousands of years ago that were transporting lead for pipes and so on. Many of them got sunk. They're lying on the bottom of the ocean. They have had that 1,000 years you need to wait. That radioactivity has decayed away, and they're sheltered from the cosmic rays because they're underwater. So there's people who go and collect lead from underwater, from old lead in old cities that's been underground, that sort of thing. And they're archaeologically interesting. So the archaeologists will take the top layer off, which has maybe the embossing of who made the lead, and the rest is just ugly old ingots of lead that get reworked into being used for lead to shield detectors, because that's radioactively pure. You have to go deep underground because here we're in a bath of cosmic rays, particles coming, hitting our upper atmosphere and just spewing out a spectrum of different particles that most of which many of which reach the Earth, but with 2 kilometers of rock, most of them will not reach your detector, and what do is a manageable level. Okay, so those are the sort of things you have to work on. Okay, so there are half a dozen different dark matter experiments underground, and they're all very exciting, but this is the one that I'm working on, so it's the one I'm going to talk about. It's the PICO experiment. There's nothing elegant about the word PICO. We used to be an experiment in Canada called Picasso. There was another one called COO. We joined forces, so we became PICO, and that was it. We work at SNOLAB. So, again, you go 2 kilometers underground. We want to be away from the active mine, so we go another 1.5 kilometers out, and we built a lab there. And in the beginning, this was the lab, just this bit. That's where snow was and our water systems and so on. And that was it. When you came into the lab here. But now we've expanded to this very large campus. I think I have a pointer. And so in here, you'll find many, many different dark matter experiments. And so one of our PICO detectors is here, and I'll mention we're building a new one. It'll go there. If you were able to, if you weren't overcome by awe and whatever of seeing the PICO detector, you could continue down the drift. You'd see a scintillating bubble chamber experiment that's being installed also for dark matter, the CUTE facility, and then there's something down there at the end. Oh, super CDMS, yes, which many of the people here at Toronto worked on. So this is a corridor just filled with dark matter experiments. And so it's a pretty exciting place, not the easiest place to work. Okay, so the bubble chamber technology, this is what our current PICO, what's called PICO 40L, but we have many different detectors, but this is PICO 40L. But the basic idea is that our dark matter particle is going to come into our detector. This is the key piece here. It's just a test tube, an upside down test tube. But it's filled with freon, in this case C3F8, and we operate it so it's superheated. That means we are operating at a temperature well above its boiling point, but it's still a liquid because it needs something to trigger that phase transition from a liquid to a vapor. And that something is going to be our dark matter particle that comes in, and I'll explain that a little bit more. But when it does do that transition, so now it's going from a liquid to a vapor, it produces a bubble. And we have cameras on the outside that will look and say, woo, there's a bubble. And in fact, when it forms, it actually makes a slight popping sound. And so we have these microphones, basically, all surrounding, there's about 20 of them down there surrounding the detector, listening for that acoustic signal. Then there's a lot which I'll go into in terms of how you actually manage the pressure and so on. So the idea is this: if you look at a typical phase diagram, if you're on the saturation curve, then you're a mixture of liquid and vapor. You're right at that interface between the two. But in fact, if you look at the Gibbs potential, it's a double humped thing, where there's a sort of a liquid-like and a vapor-like. And if you're starting as a liquid, you actually need to get some energy to go into the vapor. You have to give it a little bit of a boost of energy to get it back into the vapor. So when you're on, and this is the case when you're on the saturation curve, it's, you know, you have the same pressure, the same temperature, same chemical pressure, and so on. So everything is identical, but some is a liquid, some is a gas. So then what you do is you're going to go here and you're going to lower the pressure. So now it should be a gas, right? But when you do that, what happens is you just distort this potential initially. So as I lower the pressure, this guy goes up, and eventually it'll go up to the point where everything goes to the vapor. You can't control it. But our goal is to raise this by changing the pressure to minimize this height, but still have a barrier. That way, the trigger, the amount of energy I need, gets smaller and smaller. And so just the smallest amount of energy will cause this phase transition from the liquid into the vapor. So it's a metastable state, but it needs some energy to trigger it. So this is the worst slide in the talk. What we're fighting against is when you have a bubble form, there's a vapor inside here, but it's still got the liquid outside, and then there's surface tension. And whether or not that bubble grows to something you can see or not depends on the balance of these pressures. And that defines something. When this thing is bigger than the critical radius, then the bubble will expand forever. Well, until we stop it expanding. But the idea is, if the bubble is very small, it'll just collapse again. But if it gets to this critical radius, then it's always taking energy from the surrounding fluid, and it will start to get bigger and bigger and bigger. And pretty soon our detector is a mess because there's such a large bubble in it. It also takes, though, a certain amount of energy, and you can calculate that energy. I'm not going to go into this from this, what's called the hot spike model. But this seems to work rather well, and it's a way of us predicting where our threshold is. But the takeaway here is if you're going to form a bubble, you need to have enough energy. That will get you over the hump. But the energy can't be just anywhere in your detector. It has to be within this critical radius. And that's what saves us from gamma rays, as I'll mention it later, because the gamma rays, they deposit a bit of energy here, a bit there, a bit there. And so that energy is all distributed, and locally, there isn't enough to form a bubble. Where something like an alpha particle or dark matter will put all of the energy in one spot. So that's the key thing, enough energy within some local critical radius. So the idea is that then when that goes, even though it's a tiny amount of energy, it produces a very large effect. And I don't know how this rock has stayed there for, I don't know how many, I mean, I know what my temptation would have been, but if I saw that rock. But, you know, this is the idea. It's just a picture I, Googled picture of teetering rock, and that's what you get. But that's the idea. Once we get over the threshold for producing a bubble, it's very obvious that we have a bubble. Okay, and so this is how the detector works in practice. So we have our freon in here, and we start with this thing as a liquid, which means we have it at very high pressure. And then we're way up above the saturation curve. So it's at a high pressure, it's a liquid, and nothing is going to happen. Then we very slowly lower the pressure. And now it's superheated because we've gone from one side of the saturation curve to the other. And now we're just waiting for something to happen, like a dark matter particle. And we wait and we wait and we wait, and maybe eventually something happens and it starts to produce a bubble. We take pictures for maybe 50, 60 milliseconds. We don't want the bubble to get too big because then it becomes a problem. And after about 50 or 60 milliseconds, then we apply pressure, which is kind of an interesting thing itself. So we have big reservoirs of high pressure fluid out here. We open a valve and it shoots all that oil in here at very high pressure. That also increases the pressure here. This is a flexible bellows, so the pressure inside also goes up. So that's how we control the pressure. And then we allow it to calm down. The bubble is gone. We're all set. And then we repeat the cycle. We lower the pressure again, and we're superheated again, and we wait. And so while we see the bubble, I say we take pictures with the camera. We record the traces that come from the acoustics. And also we can watch what's happening with the pressure to understand what's going on inside. So this is an earlier detector, but this is a PICO 2L detector. What you see here are these two small chambers, and these are two little movies. And this one is what you would expect from dark matter. This indicator was probably, you see the bubble appearing. We took pictures for a while. Now it's starting to disappear because we've applied the pressure again. Right? So that's a single bubble appearing in our detector. I have no idea if it's a neutron, dark matter, or whatever, because we only have a single bubble. On the other hand, neutrons only have a mean free path of about 10 centimeters. And most of the neutron events looks a little bit more like this one, where you see these bubbles appear, and you can see that the neutron is bounced all around inside your detector. And we get up to, I think our record is like 28 bubbles or something like that from a single neutron. And the bigger your detector, the more likely the neutron is to bounce around inside there before it escapes. So although on this one, I couldn't tell you, if we only got one event, I couldn't tell you if it was a neutron or a dark matter. But if I told you most of the time, this is what we see. Let's say for every single, when we put neutrons in deliberately, we see 3 times as many multiples. If I had a signal of, let's say, 100 single bubbles, and I said, this has got to be dark matter, and Miriam said, no, I think that's neutrons. Well, we should have 300 of these events in that case. And so that's the trigger. We can know whether we have a neutron background by looking for how many multiple events we have with these multiple bounces of neutrons. And so, whereas I can't tell you on an individual basis statistically, I can say there's no chance that all those 100 are coming from neutrons and no multiples. So that's how we deal with neutrons. And as I say, they preferentially multiple scatter. I've said all of those. And then we also take great efforts to stop the neutrons from getting to our detector by putting these things in huge water baths, which tend to soak up the neutrons. Okay, so the other thing that's around everywhere are gammas and betas. And we have shown that because they deposit their energy not very locally, along long tracks, they don't deposit enough energy to trigger our detector. And where we operate down here at a little bit above 3, we have a 10 to the minus 10 suppression. And so that's what saves us. If we go lower, then yes, we're going to see gammas and betas, but by choosing the threshold, we don't see them. And then alphas is the last on the list in terms of potential backgrounds. And although you've all been taught that alphas travel basically no distance, and that's true, an alpha particle may be 50 micrometers, that's not very long, but the recoiling nucleus is much shorter. And it turns out that when you form a bubble, I said it makes a pop, the sound that it makes is proportional to the volume expansion rate squared. And so, and it turns out if you expand from a sausage compared to more or less a sphere, it's very different. And you see the acoustics are very different. So these are from alpha particles, which have a very loud signal compared to if we put neutrons in, which is effectively a proxy for dark matter. And so we can hear the difference between alpha particles. We can even do spectroscopy. The alphas have different amounts of energy. And these are the alphas that we see in our detector, the red bumps. Okay. And yeah, so on there you would say, okay, these are my alphas up here when they have above some certain noise. This is some weird parameter that we invented, but it's a measure of the acoustic power, basically. And neutrons are going to be down there. Okay, so alpha particles sound different. We can solve that, and that's a big difference for us, which is unique. Okay, so the PICO program, we've been running detectors getting bigger and bigger. So we started with 2 liters, then we had something called PICO 60. Both of these set new world best limits. I'm going to show you the data for this one. But it eventually became background limited, so we revised the design. That became PICO 40L, which is in operation, but we haven't got anything to publish yet. We're working on various problems with the usual growing pains of going to a new technology. And we're using it for an engineering to study this PICO 500, which is a much bigger detector. And that's in construction, so I can show you pretty pictures and tell you what we hope. That's it. Okay, what do we measure? As I said, camera images. That tells us where the bubble was. And so that also tells us if it's close to the wall, it's more likely to be a background. That's where all the radioactivity is. We have to measure temperature and pressure very well because that tells us what our threshold is. And then we get the acoustic signal. But when we actually run, we blind ourselves to that. So we don't look at the acoustic signal at all. That will tell us if it's an alpha particle or potentially dark matter. And we blind ourselves so that we're not biased into trying to, adjust our cuts and do our analysis in a way that we favor the observation of dark matter. So we never look at the acoustics. We do all of our analysis without looking at that. We define something called the fiducial volume, where, as I said, things too close to the wall, there's a ton of stuff on the wall from all the radioactivity. So we say we're only going to look in this box. And these are all our candidates. There are 106 of those candidates, but we don't know if they're dark matter or if they are coming from just alphas. We won't know that until we look at the acoustic data. But we draw where our fiducial volume is. We do lots of other cuts in terms of data quality and so on. And eventually, we came to this. And we could still see the neutron multiplicity, and we only had 3 multiple bubbles. I told you it's roughly a 3-to-1, so maybe there should be 1 neutron there. Could be 0. I mean, with Poisson statistics, anything between 0 and 3 would be acceptable in terms of the number of neutrons. So that's what we concluded. Then we ripped open the envelope, got the key that allowed us to look at the acoustics, and we looked at the acoustics, and every single one of those 106 events was an alpha particle. And they're all here. These are the alpha particles. And there were 0 events in the window between these 2 blue dashed lines where we would have expected, if there was dark matter, that's where the dark matter would be observed. Or if it's some nuisance background, it could be down there. And in order to get the best limit, it'd be nice to see dark matter, but if you can't get the dark matter, then the best thing is to be able to say that it's below some cross section, we're not seeing dark matter, and we can say that confidently. That becomes a problem if you have backgrounds in there. So we had no backgrounds, blind analysis, great, a world-leading limit. It produced, so these plots show, we don't know what the mass is, so we plot the cross section against mass, and basically it says, if the mass was 100 GeV, everything above this cross-section is ruled out. So all this peach-colored stuff is parameter space that dark matter cannot be seen. And I mentioned we ran PICO 2L, that was this curve here. That was a world best limit. When we went to PICO 60, a big step up in size. We came down to here. We actually had two different, we continued to run after our first publication and get more data, but eventually we became background limited by, we think, radioactivity in particulates that were getting into our detector. So that meant we had to redesign our detector to try and get away from that. So in that data, we had our freon here and water on top so that this area would not be superheated and only this part would be. But what we think happened is this flexing of these bellows maybe made little tiny bits of stainless steel, fall into the water and then eventually into the freon, and they could be radioactive or they could be the triggers themselves of bubbles. And so that was a problem. So the easiest thing to do is just turn it upside down. So now the test tube goes up, but we can't have water because that's less dense, it would float up. So now we have to keep this part really cold, so it's not superheated, and keep this part warm and it's superheated, and then we have to invent how to make a very sharp thermal gradient across here. I see I'm running out of time, so I'm going to speed up a little bit. Okay, so the status can be summed up very easily. We've run into lots of problems, mainly with chillers. We've now bought 3 very expensive chillers, trying to keep this thing cold enough. And we learned a lot along the way, but it's basically become an engineering run. We still anticipate moving into more commissioning runs and taking physics data with this detector. It actually works very well in most regards, but there are some things around the temperature control that have been particularly problematic. And so that's what we've learned as we went for PICO 500. So PICO 500 is in construction. So, but it's obviously much bigger, as the number would suggest. And with PICO 500, this is what we got with PICO 60. The PICO 40 will be a little bit better than PICO 60, but PICO 500 will push even further into parameter space. In fact, this is a neutrino background coming from neutrinos from the sun. So we'll run it for a little while until we get close to that edge, and then we'll change and move the threshold up, and then just look at this part to try and carve out this to say there's, explore that region for dark matter. Okay, this is what the design looks like. It's exactly the same, except bigger than previous ones, and it really is a lot bigger. This is a brave master student. So this is the test tube. It's a big test tube. It's made out of synthetic quartz. It took us almost 2 years to find a company who would dare to build one this big. It's really impressive that when I went down to watch them build it, it's a couple $1 million for that test tube. And this student is not really looking where he's going. He's holding this thing in hydraulic clamps. This is a couple millimeters thick, this quartz. This thing scares the death out of me. It's these big hydraulic clamps that just grab this thing and pick it up. He's got to thread it into here and then mount it on this bellows system. So he's able to do it. I don't know how he could be so calm. I would be petrified doing that. The pressure vessel is completely built. This is when we were testing it for leaks, but you get a sense of scale. I mean, this is scaffolding going up. It's just an absolutely humongous thing. It's 17,000 pounds even when it's empty before we put any oil in it. But now it's fully tested. That, what I showed you on the previous page, will get inserted from the bottom and into here. We hope that happens early this summer before what's called, there's a summer shutdown at the mine every year where they do maintenance. We'd like to have that all installed, and then we sort of start to move to commissioning in the fall and maybe towards physics by early next year. So I'll stop there just saying, you know, PICO has been incredibly successful so far. It's a very different technology using this bubble technology. You know, we've had a bit of a lull when we had to change the technology and redesign things, but we're now back on course with PICO 40 and PICO 60 coming in early 2027. There's a real opportunity for some exciting new physics. So I'll stop there. Thank you. I'm happy to take questions, by the way.
Yes, questions for Tony?
all kinds of different, if I understand correctly, all kinds of different matter that we understand leads to different kinds of bubble patterns. Don't know what dark matter is. But how can you be so sure you know what kind of bubble pattern it will produce?
So I'm not sure I would agree that we produce different bubble patterns. Basically, if you get enough energy deposited from any mechanism, you will produce a fairly normal looking bubble. I mean, it's certainly true that the shapes of bubbles can differ depending on the fluid dynamics, but that's not really related to the particles that will trigger it. So all we see is that a bubble was produced. And now, as you say, our job is to argue if we see some collection that it really is dark matter and not from some other form of background like neutrons or alphas and so on. So that we do by using a lot of different calibration sources. We also measure the neutron backgrounds and make sure it's consistent and those sorts of things. But would we learn, but to your point of are there different variations of dark matter? I mean, all we know is that energy was deposited in the detector that we can't explain any other way. That's all we can really say. Yeah.
So get to the background.
Yeah.
Sorry, so I'm just going to repeat the question for people who are online who might not be able to hear it. So okay, so the question was, once you get down to the neutrino flux background, which we call the neutrino fog, is there any hope for finding dark matter below that?
Yeah, so yes, there is hope, but it's a really hard slog. So the only way, so those neutrinos come from the sun. So if you had some way of having directionality ability in your detector, then you would be able to identify there was a class of events that all pointed back to the sun. That's unlikely to be dark matter. But it means you need to build in the capability in your detectors to see directionality. And there are people that are very active all across the world looking at exactly how you might do that. But it's hard, and largely because it's sort of a competing effort in the sense that if you want to be able to see a track, then that probably means you need to have a very low density material like a gas or something so that you can see how the track, the nucleus moved. You can pick up a track on it. The other thing you need with dark matter is amazingly dense, big detectors. And so, you will end up with these enormous detectors with maybe a few bar gas or something that you can try and pick up that directionality, but they're kind of competing effects.
Actually, I was just trying to sell Tony on a new directional dark matter detector project last evening. So thank you for that question.
Yeah.
Out of all the competitive theories of dark matter, are there any theories that particularly PICO 500 hopes to prove this?
Well, so
okay, so the question here is there a particular variety of dark matter theory that PICO hopes to prove or disprove?
yeah, so we are only sensitive to nuclear scattering, basically, that will deposit the energy, and our thresholds and so on define a mass region where we can look. So our mass region is what would be considered classical WIMPs, weakly interacting massive particles. So that's the theory that mostly that we're testing because we're in that mass range where the kinematics of a particle with that mass hitting our nucleus will give a certain amount of energy, and that's where we're sensitive to sort of that range of energies. There are many other experiments like super CMS that are trying to push that to much lower masses, and those are probably not WIMP particles. So there are, people are exploring different ones. But for us, because of our mass range, it's basically WIMPs that we're looking for. And that space is gradually being eliminated to the point where many people would say WIMPs are dead. I think there's still parameter space for that. And I think we have to do our job and finish, cover as much of that parameter space as we can. But it's not looking as optimistic as it was 10 years ago.
So if someone calls your experiment wimpy, that's not an insult necessarily.
Well, in fact, yes, at the beginning, there was a big competition between whether they were weakly interacting massive particles, which are WIMPs, and massive active galactic halo objects or something like that, which is macho. So there were the two theories, the WIMPs versus the machos. And machos were ruled out rather early. So those are, actually macroscopically sized objects that would contain dark matter in some way. Or
Yes,
would
the
be
WIMPs defeated the machos in the
Yes.
dark horse.
So are there any, presumably this, the sort of competitive edges that like PICO will spin diplet detectors because we have light nuclei that scatter off. But is there any plans on going to even lighter nuclei? Could you build a hydrogen bubble chamber?
Okay, so this is a theorist who wants to build a hydrogen bubble chamber.
it.
No, since the competitive advantage of PICO in the spin-dependent dark matter realm comes from recoils off of low mass nuclei, is there any plan to go to even lighter nuclei?
Yeah, so you called me out in the sense that I didn't mention the difference between spin-dependent and spin-independent. Spin-independent, which are most of the other experiments, are pushing quite a bit lower in terms of sensitivity, but it's possible that if the interaction depends on the spin of the nucleus, then with something like fluorine, which is an odd nucleus, then you have a window of opportunity to look there. And so there are other things like hydrogen that are also in that category. And definitely, we could never build a hydrogen bomb underground with a big vessel filled with hydrogen, but you can put in other molecules that have a lot of hydrogen in. And in fact, we've been doing a lot of work on that. We have some test chambers at Montreal, for example, where we've been doing that. And one of the nice things about this technology is it's a flask. As long as you can manage the window that you have to control the temperatures in terms of the thermodynamics, you can take that fluid out and put another fluid in. And we've been working on one exactly like that, which has hydrogen. And first opportunity would be with PICO 40, once we've used that for this engineering, would be to drain it and fill it with this hydrogenous polymer type thing. Yeah.
Yeah, at the back.
So how much sunk lead? No, that there is.
How much sunken lead do we know is actually sitting at the bottom of the ocean?
I have no idea. I really have no idea, but every experimental facility around the world seems to have a collection of it somewhere. And so, and these were, lead was being used for ammunition, was being used for pipes, and 2,000 years ago, there was a huge market of these things going to England and selling lead and stuff. And so I gather it's very expensive, so there can't be that much, but in terms of quantifying it, somebody knows the answer, but I don't.
I always tell my students, if you think you've had a failure, it may actually turn out to be useful later. Like if your entire ship sinks and it was filled with lead, hundreds of years later, that will become very valuable and expensive. Yeah, one more question?
Mike, you have already mentioned how you have to mitigate the radioactive materials sticking on the wall. How do you do that?
So the question is how to mitigate the background from radioactive materials on the walls.
So part of it's just the raw material. That's why it was so expensive. Building this out of synthetic quartz has a factor of 10 or so less than just normal quartz. But then we worry most about the fact that in the atmosphere, we have radon. Radon daughters, which are generally charged, collect onto the walls. And now we have that radioactive coating. And so we had to, from the moment these things were built at the factory to the point that we insert them, we try, for one example, we try to never allow the inside to see air. So it's sealed at all times and so on. Even then, that's not ideal. So we have a small clean room where we wash the insides in the PICO 40, and that might be one of the issues with PICO 40. We got advice from the chemists that the best way to remove that radioactivity was to use a mild acid solution. So we washed all the walls with mild acid, probably got a lot of that radioactivity off and created pits in our glass, which became nucleation sites for bubbles. So although it's not radioactivity, it's a different problem. So there's an awful lot of chemistry that goes into this, but yeah, it's all about control, mitigation, and cleaning, and to try and,
Okay, I think we have time for just one more.
well, maybe, yeah.
Like what it, like there's a set of like physical symbols that you transform.
Yeah, so basically,
Okay, yeah, so the question here is what are the actual physical observables from PICO that can then be transformed into a limit or an estimate on how many dark matter events there are?
yeah, so basically what we need to do is count how many dark matter particles we think we saw, which means effectively keeping track of the time and how many bubbles we saw. And we're only interested in events where there was only one bubble. If there were multiple bubbles, then it tells us it was probably from a neutron. So we, we count the number of bubbles to understand that difference. And really, there's not much more to it than that, counting bubbles and and seeing how many bubbles per time. Of course, then you have to fold in all the cross sections. If a dark matter particle came in, and what is the probability that it actually produced a bubble? So that goes into your calculation of the limit. But what we're trying to do is see how many bubbles we have and convince ourselves it's not coming from some other source somehow. And so one of the nice things, that was 3 months of running. And although we're taking data at probably one event every 60 seconds or a couple of minutes, so we have a ton of data, and it's all optical images and acoustic traces, so it actually fills up disks incredibly quickly. In the end, we only had 106 events to look at. And then we have a procedure where actually a lot of the students are hand scanning them, examining them all by eye to see if there's something weird about the bubble that maybe we're fooling ourselves. Maybe there's a bubble with another bubble behind that's not, properly captured by our image capture techniques and so on. So a lot of work goes into that, but it's very simple. Count the bubbles, divide by time, fold in some math for cross sections, and you have an answer.
All right, so I hate to burst people's bubbles, but we're out of time now.
We were before I finished.
So when people tell you you're doing your research in a bubble, that's not always a bad thing. Thank you very much.
You got to know.